Namaste everyone. Welcome to the physics class, second PUC physics class. Today we will discuss some problems in electromagnetic induction. Okay, so here is the first problem. A rectangular wire loop of sides 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla. So there is a rectangular coil like this. So namaste, welcome to the class. Hope you are doing well. We will move on to the problems. Here is a rectangular loop. Suppose a rectangular loop. It is having 8 cm and 2 cm with a small cut. That means it is not completely short circuit. It is opened at one point. Moving out of a region of uniform magnetic field of magnitude 0.3 Tesla. Yeah, there is a 0.3 Tesla magnetic field. Say like this. Magnetic field is like this. It is introduced and taken out. Introduced and taken out like this. How it is taken out? Whether it is taken in and taken out like this, or whether it is taken in and out like this. Whether its length is going along the magnetic field or breadth, whatever it is given. It is directed to normal to the loop. What is the EMF developed across the cut? If the velocity of the loop is 1 cm per second in a direction normal to the longer side, velocity of the loop in 1 cm per second in a direction normal to the longer side and shorter side of the loop, for how much long time the induced voltage will last. I will explain it how it is so. So we have a rectangular loop and the magnetic field, so much I think you have followed. There is a rectangular loop and magnetic field is normal to the where is it? Magnetic moving out of the region of uniform magnetic field of magnitude so much directed normal to the loop. That means normal to the loop and magnetic field are making parallel, right? It is 0 degree. Normal to the loop and magnetic field are making an angle 0 degree, so cos 0 is 1. Okay, let us move on. Suppose the magnetic field is like this. Okay, we will write the values because here understanding the situation is only the problem and the rest of the things are very easy. A rectangular loop of sides 8 cm and 2 cm. We will go for the first one. Longer side, the velocity of the loop is 1 cm per second in a direction normal to the longer side. This is the longer side. This is the shorter side, right? This side is shorter side and this is longer side. Longer side, say the magnetic field is like this. Longer side is normal to the loop means you have to put it like this, correct? Longer side is normal to the loop means you have to put it like this and take it outside. This is parallel to the magnetic field, right? So, parallel to the velocity. This is, if the velocity of the loop is so much in a direction normal to the longer side. Velocity is like this, normal to the longer side. Velocity is like this, normal to the shorter side. Okay, so how do we show the coil? As it is like this. Coil is shown like this. You have to show the coil like this. It is put like this, and say like this. It is taken into and out, and the magnetic field lines are passing normal to the coil. Hope you can understand it. It is actually like this, right? And velocity, it is introduced, right? A rectangular loop of side 8 cm and 2 cm small cut is here, right? With a small cut of a region directed 0.3 Tesla B, 8 cm, 2 cm. What else? I want a longer chunk, yes. And what is the developed cut if the velocity of the loop is 1 cm per second in a direction normal to the longer side. It is introduced V is equal to 1 cm per second in a direction normal to the longer side. How long does the induced voltage EMF? Yes. Now the condition for the coil is it is in a complete out of magnetic field. No magnetic field through this. As it is introduced, it is getting full flux. And how much time does it take to completely go into the coil? When the into the magnetic field. When the coil is here, remember, when the coil is here, no flux, no magnetic field. When it is introduced into the magnetic field, full flux. When it gets full flux, when its complete area is introduced into the magnetic field, am I right? How much time does it take to completely get into the magnetic field? How much time is taken to move this 2 cm into the magnetic field? Because this part is normal to the magnetic field. This part is, say, I will put the magnetic field normal to you. That becomes easier. The magnetic field is coming towards you. Now when I put it like this side is normal. However, that gets introduced into the magnetic field simultaneously. What about this part? When this part gets introduced, there is a time for 2 centimeters to introduce itself. So what is the time taken for 2 centimeter length of the coil to get into the magnetic field? So velocity is equal to displacement by time. Velocity is 1 centimeter per second. Displacement required is 2 centimeter. What is time taken? This is 1 centimeter per second, right? So the time taken is 2 seconds. 2 seconds are needed for the coil to get completely immersed in the magnetic field, because this side should get into. This side, however, it enters simultaneously. Now, what is E? And by 2 seconds, the complete coil will be inside the magnetic field. Before 2 seconds, the complete coil was outside the magnetic field. So, E is equal to d phi by dt. Am I right? And it's only one turn, n d phi by dt, but it's only one turn. So, this is the small cut, otherwise it's a short circuit. Okay, now, what is phi? Phi is n a b omega. Right? Oh, sorry, flux is NAB cos theta. That is NAB omega in a dynamo. NAB cos theta. What is NAB cos theta here? Cos theta is cos 0, because all the magnetic field lines are normal to the plane of the coil, and theta is angle between the normal to the coil and the magnetic field. Phi is maximum. This is phi maximum. Phi minimum is 0, right? Phi minimum is 0. That is when it is here. Phi maximum is when it is completely immersed. Phi maximum is equal. Number of turns 1. Area, length into breadth. 16 into 10 to the power minus 4. 8 into 10 to the power minus 2. 2 into 10 to the power minus 2. 16 into 10 to the power minus 4. Breadth, magnetic field. Magnetic field is 0.3 Tesla. Cos 0 is 1. Right? Cos 0. Because normal to the coil and magnetic field both make same direction. So what is the maximum flux introduced? Phi maximum is equal to NAB cos 0 cos theta, that is 4.8 into 10 to the power minus 4 Weber. WEBER. Weber is the unit of flux. Now phi minimum is 0, phi maximum is this much. What is induced EMF? Is equal to d phi by dt, that is phi maximum minus phi minimum, maximum to minimum, divided by time taken. Phi maximum minus phi minimum is 4.8 into 10 to the power minus 4 minus 0 by time taken is this 2 seconds. 2 seconds, that is equal to 2.4 into 10 to the power minus 4 volt. How long does this, for how long does the induced voltage last in each case? Okay, here it lasts only for 2 seconds, because when you introduce this, the change in the flux starts only when it gets introduced, because 0 flux, 0 flux, 0 flux, 0 flux. Flux has started increasing, right? This change will occur only for 2 seconds, because 1 centimeter per second velocity with which it is entering, and to cross 2 centimeters it requires 2 seconds. So up to 2 seconds the flux will be changing. Once it gets completely immersed inside the magnetic field, then there won't be any change in the flux. There is flux, but there is no change in the flux. So it continues with the same flux, no d phi, so d phi by dt is 0. So that is, it lasts for 2 seconds. Now second case, shorter side normal to the velocity. If the velocity of the loop is 1 centimeter per second in a direction normal to shorter side, like this way you have to introduce this, like this way. So if it is shorter side, of course this won't change, this will be same. But how much time does it take? Now velocity is equal to 1 centimeter per second, displacement, now the shorter side is normal and longer side is entering, it is 8 centimeter per second. So it was like this, right? And now it gets introduced like this, longer side. 8 centimeters should get in. When 8 centimeter gets in, its displacement is 8 centimeter by time taken is 8 seconds. Now only this change, E is equal to d phi 4.8 into 10 to the power minus 4 divided by dt, 8 seconds. It is 0.6 into 10 to the power minus 4 volt. and it lasts for 8 seconds because there is a change up to 8 seconds. So simple it is, right? The problem looks very longer, very horrible, but very simple. You are just introducing a coil and thereby changing the flux linked with this. Once it is completely introduced, no change. Once it is outside, no change. As it is introduced, there is a change. That's why it is for 8 seconds, because to cover 8 centimeters into the magnetic field, it needs 8 seconds. Okay, very simple. Okay, we will move on. Yes, here is the remote. Second problem. A circular coil of radius 8 centimeter and 20 turns is rotated. Okay, put up this. Rotated in a magnetic field, rotated with a vertical diameter with an angular speed of 50 radians per second. Vertical diameter means diameter is vertical to the magnetic field, right? Suppose the magnetic field is like this, coil should be turned with this diameter vertical to the magnetic field like this, right? So coil should turn with its diameter vertical to the magnetic field. In a uniform horizontal magnetic field of 3 into 10 to the power minus 8, or you can say that the horizontal magnetic field and vertical diameter. Obtain the maximum average and EMF induced in the coil if the coil forms a closed loop. It is very similar to the dynamo coil, but it is a circular coil, that's all. Suppose the magnetic field is horizontal and like this, say, I will turn the coil like this way also, vertical diameter. So diameter is vertical to the magnetic field. B is how much? 3 into 10 to the power minus 2 Tesla, right? And this is rotated at 50 radians per second, 50 radians per second, all SI system. As it turns, when the coil is like this, no flux. When the coil is like this, maximum flux. When the coil is like this, no flux, maximum flux. So what is the maximum? This is dynamo coil itself, right? In what the dynamo we have studied, it is rectangular coil. Now it is circular coil. The peak value of EMF induced is NAB omega. Remember the formula? Make a list of all the formulas. What is EM? EM or E naught is equal to number of turns in the coil. A circular coil 8 centimeter, 20 turns. Area pi r squared, right? Radius is 8 centimeters. So pi r squared. Pi 3.14. 8 centimeters squared. 64 into 10 to the power minus 4 into B, strength of the magnetic field, 3 into 10 to the power minus 2. Omega, angular speed, 50. That is the peak value of EMF. EM is equal to, a left calculator here. Last time I didn't use calculator for the first problem. 20 into 3.14 into 64 into 3. NAB omega, that is the peak value. Where do they obtain the maximum and average EMF induced? Maximum and average EMF induced, we are not getting that answer. E naught is 0.603 volt, somewhere we are gone wrong. Pi r squared, right? 20 N A pi r squared B omega 50. Everything is over. 20 turns, yes. Pi r squared, yes. 20 into 3.14 into 64 into 3 into 50. NAB, yes. We are getting now. Into 10 to the power minus 4. So minus 6. 602,880 into 10 to the power minus 6 volt. That is equal to, did I write it down? Okay, minus 6. 1, 2, 3, 4, 5, 6. 0.62 volts. That is the peak value. Average value of EMF induced is 2 by pi times the peak value. Know this one? Average value is 2 by pi times peak value. So into 2 divided by 3.14. That is equal to 0.384. Is it so? Yes. 0.384 volt. Average value of EMF induced. Then, if the coil turns in a closed loop of 10 volt, calculate the maximum value of current. IM is equal to VM by R. because only resistance effect here. Vm or Em by R. Em is 0.62 divided by 10. Oh, it becomes easier. 0.062 amperes. 0.062 amperes. 0.62 we have got. Is it 0.62 first one? Because we have 0.603. Let me check it once again. 20 into 3.14 into 64 into 3 into 50. 0.602, sorry. 0.602. This is 602. It is not 620. It is 602. So it is 0.602. 0.602 into 2 by pi, that also into 2 divided by 3.14. Oh, that came correct because I retained that value. While writing this, I made wrong, but the value that was here was correct. Okay, 0.602 by 10. 0.0602 ampere. That is correct. Then what else? Power. Calculate the average power loss due to Jowl heating. Power is equal to, actually we should calculate it as Vrms into Irms. Actually it is not V into I. Hope I've done it wrong. Calculate the average power loss. Average power loss is Vrms into Irms. That is equal to, peak value is 0.602. Peak value of voltage is 0.602 by root 2 into peak value of current is 0.0602 by root 2. That is equal to, so 0.602 into 0.602 into 0.0602 is equal to, divided by 2, right? Divided by 2. That is equal to 0.018 watt. Yes. 0.018 watt. Hope you have understood, because once you study alternating current, these things are very easy. Average power is only Vrms into Irms, since it has got some resistance. Vrms peak value by root 2, 0.602 by root 2. Irms peak value by root 2, 0.0602 by root 2. So this becomes 2. So 0.018 watt. From where does this calculate the average power loss due to Jowl heating? Where does this power come from? From the mechanical energy with which you rotate. What the energy you have spent in rotating the coil is lost in the form of heat, like this. Power loss comes from the external mechanical power used to turn the coil. So in hydroelectric generator, we use that mechanical energy, or we get the mechanical energy from the potential energy of water, which falls down and gets converted into kinetic energy of the turbine, and then we use to rotate it, and that is converted into electrical energy. Okay, problem number 3. Right. Current in a circuit falls from 5 ampere to 0 ampere in 0.1 seconds. If an average EMF of so much is introduced, 200 volt, then give the estimate the self-inductance of the coil. Magnitude of EMF induced is L di by dt. EMF induced is 200. L, don't know. Di is 5 ampere to 0 amperes. 5 minus 0. Time taken is 0.1 seconds. Over. Problem. 200 into 0.1 divided by 5. That is 20 by 5. 1 0 here. Sacrifice. 4 Henry is the self-inductance of the coil. Correct answer. Okay. We'll move on to the fourth problem. Right. This is the fourth problem. A jet plane is traveling towards west at a speed of 1800 km per hour. So jet plane is moving like this, say. Its wings have a span of 25 meters, right? What is the voltage difference between the ends of the wing having a span of 25 meters? If the Earth's magnetic field at the location has a magnitude of so much Tesla and the dip angle is 30. Yeah, the aeroplane is moving like this. As it moves like this, the wings of the aeroplane will act like a conductor and a rod which is cutting the Earth's magnetic field lines. Which Earth's magnetic field lines? Vertical component. Vertical component is cut like this, and you know, if the magnetic field lines are cut like this, if the magnetic field is normal to the plane of the board like this, and we have done this and we have derived if there is a conductor here and if a rod is moving like this with a speed v, it cuts these magnetic field lines. This rod is cutting these magnetic field lines. What is the EMF induced? BLV. The same situation is obtained here also. When the aeroplane moves like this, the wings will cut the normal component of Earth's magnetic field, and the dip angle is given here. You see, Earth's magnetic field lines are like this. Dip angle theta is how much? Say it is 30 degrees, right? Dip angle is the dip angle is 30. So which component? This cos component or sine component? It is sine component. So this is the vertical component, which is B sine 30, which is cut by the aeroplane wings. Aeroplane wings will cut this one. So that has to be used now. So BLV, B is E is equal to, this is BH, sorry, Earth's magnetic field, BE sine 30, dip angle, vertical component, because dip angle is the angle made by the true magnetic field with the surface of the Earth, that is 30. True magnetic field will be like this, and it makes an angle 30 degree with the surface, that is dip angle. So vertical component is B sine 30, B sine 30, L, V. Induced EMF, BE, that is Earth's magnetic field, is 5 into 10 to the power minus 4, half, length of the coil is, length of the wings are 25 meters, and speed is 1800 into 60 in, 1800 kilometer per hour. 1800 kilometer per hour. 0 will get cancelled. 6 300s are 650s are. So what is the answer? Induced EMF is equal to 5 into 25 into 50 divided by 2. 3125. 3125 into 10 to the power minus 4. Into 10 we have one more, 10 to the power minus 3. This one and this one. That 10 I have not used. Okay. Then what is the answer? That is equal to 3.125 volt. That is the EMF induced. Yeah. So even you can apply this problem for a vehicle moving on the surface of the Earth. Its axle will cut the magnetic field lines. So that will also induce an EMF in the vehicle. A train moving in a track, that will induce EMF because it can be taken as a conductor. 5. Peak value of EMF is 260 volt. Find its RMS value. Very simple. Peak value is 260. So ERMS is equal to 260 by root 2. That's all. Just for reminding, I put this 260 divided by 1.414. That is 183.87. Yes, 183.87 volt. Next one. The magnetic flux passing perpendicular to the plane of a circular coil varies according to the equation phi is equal to 3t square plus 4t plus 1. It is given in the form of an equation. Magnetic flux varies according to the equation. Phi is equal to 3t square plus 4t plus 1. Where phi is in milliwebers, okay, flux, and calculate the EMF induced in the coil when t is equal to 3 seconds. What is the induced current in the coil if the resistance of the coil is 10 ohm? Okay. Induced EMF is equal to d phi by dt. I will calculate only magnitude of induced EMF. That is d by dt of 3t square plus 4t plus 1. Magnitude of induced EMF 60 d by dt of 3t square plus 4 when t is equal to 3 seconds, E is equal to 6 into 3 plus 4, E is equal to 18 plus 4, that is equal to 22 volt. If it is 20, millivolt, because this is milliweber per milliweber, so this is millivolt, because this is milliweber, right? This is milliweber, phi, so millivolt. What is the current? Current is equal to what is the current, induced current in the coil if the resistance of the coil is 10 ohm? 22 E by R, 22 millivolt divided by 10, 2.2 milliampere. That is the thing. Okay, 7. A 1 meter long metallic rod is rotated with an angular frequency of 400 radian per second. Okay, about an axis normal to the rod passing through its one end. Can you guess how is the situation? Why this cord? A 1 meter long metallic rod is rotated with an angular frequency of 400 radian per second about an axis normal to the rod passing through its one end. You have to take the rod and you have to pass an axis normal to the rod passing through one end, and it should turn like this. Hope you have followed this one. The rod is like this. Axis should be normal to the rod but not in the middle, at one end. So it should turn like this, isn't it? So it should turn like this, and it should turn in a magnetic field. About an axis normal to the rod passing through one end. The other end of the rod is in contact with a circular metal ring. A constant and uniform magnetic field of so much Tesla is parallel to the axis. You see, the situation is very simple. You can guess it yourself. Magnetic field should be parallel to the axis, right? Shall I show it like this? This is rotating. This is the axis at one end, and it is turning like this. Magnetic field is parallel to the axis means it should be like this, right? Everywhere. That means this rod should cut all the magnetic field lines. Okay. Can I show the situation like this now? There is a ring in order to have the contact of the rod, and the rod is attached here like this. This is the rod. This is the center, O. And the rod is rotating like this. Axis of the rod is perpendicular to the plane of the board, and the magnetic field is everywhere like this. That is B. Normal to the plane but parallel to the axis of the rod. Rod is turning like this. Now the situation is so, and it is given 1 meter long rod. Okay, the total length is 1 meter. Okay, and it is rotated with an angular frequency omega as 400 radian per second. Okay, about an axis normal to the rod passing through the one of its end. The other end of the rod is in contact with a circular metal ring. So this is just a contact, to have a contact, and metallic ring. A constant and uniform magnetic field of 0.5 Tesla is applied normal to the rod but parallel to the axis. Calculate the EMF developed between the center of the rod and the ring. Yes, what is the EMF developed? So I will take a wire from here and also from here. What is the voltage induced here? Okay, now the formula for induced EMF is BLV, but the data is omega here, and of course omega is same for all the parts of the rod, but V is not the same for all the parts of the rod. See, this part of the rod which is at the extreme end will be having more velocity or speed than the part of the rod which is here. Here this part of the rod which is at the center will not be moving at all. It will be just rotating about an axis, or on the axis it is rotating. But for this one there is no radius. For this one this is full radius. So speed is different. Now how to go along with this one? Now you can go for integration. What I can do is, I will do it like this. Of course, better you know how to solve this through the integration. Of course, you can make a very simple conclusion here also. I will say that at the end. Now, the whole rod, you take it as a full rod of length R, that is radius. Now, consider a small piece of the rod here of thickness dx, which is lying at a distance x from the center. For this part of the rod, radius is x. Am I right? For this part of the rod, radius is x. For this part of the rod, radius is capital R. For this part of the rod, radius is 0. So it is very difficult to find out the length of the rod here. So take a small length of the rod dx, which is rotating at a distance x on the whole rod. Now what is the induced EMF for this rod of length dx turning in this circular path like this, right, here with the speed v? What is this? And this speed v may be the speed of this particle, or this piece of the rod. That speed may not be the same for all the parts of the rod. This will be turning with more speed, this will not be turning with no speed at all, zero speed. So what we will do is, we will take this sample and find out what is the induced EMF D for this rod. D is equal to, magnetic field is a constant, the length of the rod is dx, right, length of this rod. Speed for this one is V equal to R omega, I will write. V is equal to R omega formula. Radius of this piece of the rod is x. Omega is same for all the parts of the rod. Angular speed is same. So when a rigid body turns, when a fan turns, the one part of the fan, if it covers by 30 degrees, all the parts will cover by 30 degrees. So the angular velocity is same for all the pieces of the rod. Whether I consider the piece here, here or here or here or anywhere, it is one and the same. But the length of the rod is dx. This is a small rod moving in a magnetic field, cutting the magnetic field lines which are normal like this. And that piece is taken as reference, which is lying at a distance x. For that induced EMF, small induced EMF is B, which is a constant everywhere, at the length of the rod dx, and its velocity is V equal to R omega, R is x omega. Now, what is the, so I will write it as B x omega or omega x dx. This is D. What is the full E? Full E is the integration of this. Integration, such pieces taken from 0 up to R. Full radius is R, right? Taken from 0 up to R, B omega x dx. This is a constant, that is equal to integration, B omega integration from 0 to R x dx. But that is equal to B omega. What is the integration of x? It is x squared by 2, x to the power n plus 1 by n plus 1, 0 to R. Upper limit is R, lower limit is 0. When upper limit is R, induced EMF, full induced EMF is equal to B omega R squared by 2. Isn't it? This is R squared by 2 minus 0, that's all. Upper limit is B omega into R squared by 2 minus 0. Because when you put 0 lower limit, it becomes 0. B omega R squared by 2. This is the induced EMF. You can do it like this way also. You see, when you take a piece here, a piece at the end, its velocity is V equal to R omega, right? Full R omega. What is the velocity of this piece? 0. What is the average velocity? Average velocity is R omega maximum, minimum is 0 by 2, R omega by 2. Substitute R omega by 2 here. Length of the rod is also R. R omega by 2. What you will get? B R square omega by 2. Same thing. But this is the best method. Whatever be the situation, integration holds good. B R square omega by 2. So what is the induced EMF? That's all now. Induced EMF is equal to B, what is the strength of the magnetic field? 0.5 Tesla. R square, radius square, omega is 400 radians per second. R square, what is the radius square? The other end of the rod is in contact with the circular ring parallel to the axis, everything is given. 1 meter long rod, R square, omega by B omega R square by 2. This is 200, one sacrifice here, 1 0, 5 into 20, 100 volt, no calculator. Yes, correct answer. So this is one idea how to, you see, one concept, when a rod moves in a magnetic field, EMF is induced. That is one concept. But applications in different ways, right? You must be able to put in different ways. One method is here. So when the whole rod moves, this part of the rod is having different speed, this part of the rod is having different speed. So take a sample of the rod, let it be at a distance x. What is its speed? V equal to R omega, R is x, and the length is dx, and then integration gives the answer. So that is the last problem, I think. Yes. Yeah, that is the end of the problem, and we will have few more problems later in different ways, right? So this chapter is very good chapter for entrance exams. We have few small formulas, but the applications in different ideas. So you must understand the theory behind this. Hope you have followed all these problems. Thanks for watching the class, and we will meet in the next class with different problems. Thank you.